Today's lecture is on logarithms and exponentials or exponential functions. Logarithms are also functions. Before we define logarithms and exponentials have a large number of applications: sound intensity, level in decibel, dB, Richter scale for earthquakes, populations changes like growth or decay, for example human populations, cells, bacteria, how bacteria grow, that can be expressed with an exponential function. Radioactive decay, same thing. Quantum mechanics, chemistry, pH, all of these are some applications of logarithms and exponentials, but they do have a lot of applications, not just these. Let us take the function f of x equals 1 over x. The graph of the function looks like this. When x equals 1, y equals 1. This is the x-axis, this is the y-axis. So the graph is in two parts like this. Okay. If you take any function at random with a graph that looks like this, we can always find the area under the graph, this area here, by doing this integral. Okay, don't worry about what an integral is, because it's not today's lecture, and you don't need to know what an integral is to be able to understand logarithms. Okay, this is called a definite integral between a and b of f of x with respect to x. So when you calculate this, that gives you the area under the graph. Okay, so if we wanted to calculate the area under this graph, then we would integrate 1 over x dx. And one of the formulas that existed before for calculating that integral is this. And again, don't worry about the integral. This is what the formula looks like. If you use this formula, this is the integral of x to the power n. So that could be x squared, x cubed, x to any power. The result of this integration is x to the power n plus 1 over n plus 1 plus c. But in this formula, n plus 1 can't be 0. So that means n cannot be equal minus 1. It can't equal minus 1. When n equals minus 1, that's exactly the function we're looking to integrate. When n equals minus 1, x to the power minus 1 is the same as 1 over x. Okay, this is the function whose graph I just showed. This graph. If we wanted to find the area under this graph, okay, the area exists. Here it is. The area exists. But you cannot determine it using this formula because n is equal to minus 1. It exists. Same thing with the integral of 1 over u du or 1 over y dy. So what do we do? I mean, the area exists, but we can't find it using this formula. A new function was invented, and it was many centuries ago to do just that. And the function was invented to allow us to find this integral without using this formula. So the function is like this. The integral between 1 and x of 1 over u du. Okay, we can't use this formula to do it, but we know it exists. Since it exists, they had to invent a new function to represent it. And that function is ln of x. ln is the logarithm. So the logarithm is just a definite integral. Okay, ln is called the natural logarithm. And the function corresponding to it is called the natural logarithm function. Okay, the area was the area under the graph on this side, the positive side. That's just taken by convention. They could have taken this side, but they only took the positive side. So therefore, the logarithm is only defined for x between 0 and plus infinity, not at 0. So the domain of the logarithm function is, okay, domain d equals 0 to plus infinity. Okay. The logarithm of 1 is equal to 0. And the logarithm of any number is the area up to that number. So for example, what's the logarithm of 2? Okay, to find the logarithm of 2, you locate 2 on this graph. And you find the area under the graph between 1 and 2. Whatever that area is, that's the logarithm of 2. It ends up being 0.693. I'll write it in a minute. To find the logarithm of 3, same thing. You measure the graph from 1 to 3. Okay, the logarithm of 2 is 0.693 approximately. And then the logarithm of 3 is approximately 1.0986. So we'll approximate it to 99, etc. Between 2 and 3, the logarithm reaches a value of 1. So at some point between 2 and 3, let's call it e, the logarithm is equal to 1. At that point, e is a special point, and it's an irrational number. It's approximately equal to 2.718. There's more decimals. 281828. It's not repeating, by the way. This is an irrational number. The logarithm of this e is equal to 1. Any number that is greater than 1 has a logarithm that is positive. And when x is less than 1, its logarithm is negative. For example, ln of 0.5. This is approximately negative 0.693. And when x equals 1, the logarithm is 0. Okay, next we're going to go over some properties of logarithms. The first property is the logarithm of a product, ln of xy. ln of xy is equal to ln x plus ln y. For example, ln of 6. 6 is 2 times 3. We can write it as ln 2 plus ln 3. Why is this important? In the beginning, they did not have logarithms tables, so they had to do this to calculate them. They didn't have calculators like we have now. Okay, when you add these two logarithms, this is what you get for ln of 6. You can check it. ln of x over y is ln x minus ln y. For example, ln of 2/3 is ln 2 minus ln 3, and it ends up being minus 0.405, not 6, okay? Because here we have approximated. There are more digits after the 3 and the 9. This is why it comes to this. ln of x to the power n is n ln x. For example, ln of 3 squared is 2 ln 3. And this ends up being 2.197. Other logarithms. Let a be a number that's greater than 0 but not equal to 1. The logarithm of x in this number, this is called a base. In base a, so we're going to call a the base, is equal to ln x divided by ln a. For example, if you're looking for log 50 in base 2, then you divide log 50 by log 2. Log 50 is 3.9120. Log 2 is this. Divide them, and this is the number you get. When the base is 10, log x in base a is log x in base 10. But when it's 10, we don't write the base. We'll just write log x. If you see this notation, log, this automatically means log in base 10. If you see ln, it's log in base e. E is the number from earlier. So for example, log of 100,000 means log of 100,000 in base 10, which is equal to 5. Log of 1,000 is 3. Log of 10,000 is 4. Log of square root of 2 in base square root of 2 is equal to 1. Let's do some examples. Simplify these. Log of x squared times y cubed. The properties of ln also apply to log in any base. So this is a product. The log of a product will be the sum of logarithms. So you separate them. It will be log of x squared plus log of x cubed. But log of x squared, we can take this 2 out to the front. So it ends up being here. It will be 2 log x. And this will be 3 log y. Done. For this one, ln of x to the power 6 over w squared, separate them. It will be ln of x to the 6 minus ln of w squared. Then take the 6 in front, 6 ln x minus 2 ln w. Done. For this one, we have a product here divided by something. So first you do, it will be ln x plus ln of 4th root of y. These two are in the denominator, so it will be minus ln of z squared minus ln of w cubed. It's minus because it's in the denominator. 4th root of y is the same as y to the power 1/4. ln x, we just bring it down. Now for this one, you bring out 1/4 ln y. Here you bring out the 2 ln z minus 3 ln w. Done.